If you have two objects here, for example, one at 0 meters per second, one at 5 meters per second, and 5 meters per second, 0 meters per second objects hit. And this one is, because this one's reaching 2 meters per second, this one must be 2 kg because it only pulled by 2. This one's 3 kg. Obviously, it could be multiples, like this could be 4, this could be 6, but the same idea. Where this object, this one's pulled in all the way to the 2. This one's pulled only just to the 2. And we're just focusing on this object. And if you were asked, for example, what would be the change in, as in, what is the momentum that this object has lost? Well, its original momentum was 5 times 2. So its original momentum was here, 5 times 2, so it's mass times velocity. And then its new momentum is mv1. This is v1 here. I'm just going to label these like kind of like as though they were separate to the 5 and the 2 and the 0, like if they had their own values. I'm going to label this vx because it might not be 0. I'm going to label this v. Now, so mv, this would be m, and I'll label this m2, or mx would make more sense. So mv, take away mv1, like that, and I would get m1, not m1, m is equal to v take away v1, and that is the momentum lost. As you know, momentum is conserved, so that would also be the momentum gained on this side. So we've kind of like forgotten about the Vx, which is quite nice because we don't want to think about the Vx. The momentum gained by the other side should be equal to this. This is the mass times by the, v take away v1. Now, when we're working stuff out, and we wanted to work out that change in momentum, we can find the old one and the new one, but because it's going to act elastically, the rods are going to connect, they're going to act inelastically, and then they're going to act elastically. So we can't it'll be very difficult to find the velocity because we'd have to draw kind of like a curve of, for example, this object was going from 5 to 2, so it'd be decelerating. So it'd be watching it decelerate, and we'd have to find the velocity it hits before it's released, and it just decelerates even more. So you'd have to find the velocity when it's released, which would be really difficult. So we can just try and find the, I guess, the average velocity, and say that that's its total kinetic energy is what we do. So we basically find its original velocity, and it will go to a new velocity. The new velocity is what we actually care about. Ignore these labels of v1 and v2, it's just the old one and the new one. This is actually v, and this is v1, which is the 2, so this is 5 to 2. And basically what we do is we say, okay, going from 5 to 2 meters per second, so the distance it would move would be 5 so this would be 3, because it's 5 to 2 and the v is across that way, and then this would be 1, so 3 meters per second, 1, so the distance would be 3. The distance wouldn't be 3, sorry. The distance would be the area under the curve, which would be 1.5. And then the time would be 1 second. So it would move 1.5 meters in 1 second. So we would say that instead of saying that the change in velocity v take away v1 is 3, what we actually say is that it's 1.5, because this is easier to calculate. So 1.5. So what we're saying is the velocity change that it I know. We would not need to half it if we were using C, because a photon would immediately be absorbed, and then like if it wasn't another massless photon, I don't know, with 0 meters per second, which wouldn't be possible, but whatever, it would accelerate it to C immediately, and then they would separate, so it would give it all of its energy, including the C part. And so in that case, there would be no halves. That's why we get mc squared instead of half mc squared. Get mc squared for the energy of an object if it completely turned into photons. But we half it in conventionally in kinetic energy. But if we ignored the half, because the half is just like us calculating it, let's just ignore the half. But you know why the half is there. The half will be coming with this v take away v1 thing. But it's fine because the half kind of follows everything, if that makes sense. So you might as well attach the half to the m. So we find out that what's the total energy then? Because that's what we're trying to work backwards to get. And we have the total energy. Let's just go back and say, what's the total momentum? We have the momentum loss, so we have P loss, and we know P loss is V take away V1. We know that the total momentum is MV, because this was 0, but the total momentum might just be what's it called again? The difference in MV. Which normally is how you'd usually work it out, because you'd have the force times by the distance, so you'd have the overall force forward. So let's just assume that this object is 0 meters per second, so we're working out the momentum given from the overall force forward. That's why I said Vx. I set the Vx to 0 here, even though other circumstances it might not be 0, but we used force because then we can work out an overall force, overall momentum change, and then we'd know what's called again with the overall momentum change, like we talked about the distance, which is half of what it should be, because that's it's an annoying factor of distance, because of the change in velocity, and then it's the area under, and the area under is a triangle. If deceleration or acceleration is constant. So the force part would find the difference. So we're just going to use mv here, even though you could say, oh, but the overall momentum is mv take away mvx, right? And that's true. But we're just gonna ignore it for now, because mv plus mvx, but vx is 0, because we're finding a situation where there's a change in momentum overall of that, so everything's just kind of been shifted along, because the difference is the same, the energy change is the same, it's just we start at a different point, so we've just shifted everything to 0. So mv 2 times 5 is equal to mv take away mv1, which is the momentum lost. We know mv is the total momentum. We know the momentum loss. So what is the momentum kept? Was mv1, and we know that because it's reached v1. It has its same mass, so mv1 is its momentum kept. Now, if this is the momentum that it keeps, this is the momentum that it's lost, but also the momentum to the new object. And that's nice and all. But what we want really is the energy. So all we do to get the energy, well, we know that what's it called again? We could technically multiply everything here by the same thing, which is why the half doesn't really matter. But if you see here, when we calculate it, we got like half of this. We'd get half of this because we'd be going from v to 0 to calculate this. and we'd be using, and when we get here, we would try and calculate the momentum lost. We'd only be able to use the distance, which is really annoying, because the distance would only be half of the distance divided by the time, or just the force times by the distance. But the force is mv divided by mv divided by t. So then the divided by t would be shifted along to here, which is the same as mv times by another velocity. But this velocity is half because it's a triangle. So we're using the half v here. So we half mv. So half mv. And we have the, so then this is half so m, oh wait, let's ignore the half for now, but that's where the half will come from. Now when we have all of this, right? This is lovely, but we want energy, and energy is energy wants to take into account proportions. So if you see here, this would be 3, wouldn't it? This would be 2. So this would be 3 times this one's mass, 2 times this one's mass, and this would be 5 times the mass. So 5m, 2m, no, 3m plus 2m. And we can find out how the energy, everything's split, right? What we're actually finding out is how much kinetic energy, or I guess how much momentum it has. And then energy is like a state, like you have energy in you. So you might think, but this one, I don't know, this one, the P loss is huge, but for it to have lost it, then this one must have gained a lot of energy. But it didn't really increase by that much. And if you remember, heavier objects require more energy to get to the same velocity, aka they have more inertia. So high velocities of the other object, you'd require even higher velocities than an object of the same masses if one object has a lower mass for this one to react. So it required more kinetic energy for this one to change its velocity. So it makes sense that it gained a lot of kinetic energy but had a very small change, because this one ended up keeping very little of its kinetic energy because it was trying to move such a heavy object, or a heavier object, to its velocity. Now, this is all well and good, but we want something that doesn't take into account losses. For example, if you see here, v take away v1, for example, we want this to always be a positive. For example, here, v take away v1. What's it called again? Let's say this was -5, this one was -3. The energy loss, the energy loss is the change. So it's the 5 take away the 3. It's the, so something goes from -5 meters per second to -2 meters per second. All that's happening is that it's gaining 3 meters per second in like the right direction. So what's it called again? It's gained energy in that sense. And so if it's gained energy, then the energy loss of the object causing it the other object would lose energy, but because of all the negatives, this would be the, let's say there was an object of -5 meters per second. Screw that. If this was this was trying to work out the difference, then we would need the large one, so -5 minus 3, the difference would be -2 mv. And so for that to happen, the other object, let's say it went from 1 to -2, then it lost -3, so it'd be 1 minus 2, which would be 3 times, so 3m. This object started at 1 m, as you can see. Now its velocity went from 1 to -2, right? 1 to -2. And the other object went from -5 to -2. So this object caused this one to accelerate, but in turn it caused this one to decelerate. This object's original mass, let's say, was 5. It doesn't matter about the other one. And this said, so we'd have 5 here, 5 times 1, which we don't have to really think about this. So we just see the change in velocity. And the change in velocity here would be the original, take away that, so that would be 3m. Well, the energy loss is 3m, but it originally had m, right? Okay. What about here? V1. Well, V1 is -2, so you'd have -2m, or 3m minus 2m equals 0. Oh, well, that's kind of annoying, because, like, what is this telling us? It's telling us that the other object I'm sorry, this is the energy loss, this is the momentum it's kept. So the momentum at the end is -2m. And the momentum it lost was, so it gained, its momentum it is -2m because it lost a momentum of 3m, which makes sense because of these two. Its original momentum was 1m. It gained a momentum. Original momentum was 3m. It ended up with a momentum of -2m. So it must have. So original momentum was 1m. It ended up with a momentum of -2m. So it gave away, or it lost, a momentum of 3m. Cool. Now, all energy is, and you might start to see it. The halves are because of this, how this is measured. So I could just put half in front of everything right now because this is half, this is half. And because if you did half mv, take away half mv1 minus v2, you'd end up with half that is your halves. So you might start to realize, oh, the only real difference so far between this and the original, because this is energy, like this is the work done, and you might have realized that, oh, when we're calculating it, you have half mv, and then we find out like the velocity, like during the interaction, you know, how much velocity did it gain, like lose or gain or whatever. How much energy did it lose or gain? You take away, so this is its end energy, and so you'd go, okay, then this is the energy it gave to, or the momentum it gave to the other object. And of course, if this v is equal to this v, then this would be 0, which makes sense because if an object goes in with the same momentum it came out with, then it must have lost no momentum. Same way here, let's say this was energy. Just imagine for a second it was energy. If this had, like, if this was all of its energy and then this was half of it, it came out with half of its momentum, half of its energy. So all the halves is how we calculate the velocity. So had this much momentum, came back with half of its momentum. It ends up like what's called must have given away half of its momentum. But the problem with momentum is that because the share of momentum is pretty cool. So for example, this object here, 3 times 2, the V1, which is 2, is it's so 6 joules. And then this one's 2 times 2, so 4. If we were using momentum as its energy indicator. So this one had 4 joules left. It gave away 6 joules. We want to work out this one. Energy doesn't use velocity. It doesn't use that, sorry. We don't use momentum for energy. We use, like, we want a sort of ratio-ness to it. So let's just write out what we had here. See, half mv, half v minus 1v. This here, mv, and then mv minus v, blah, blah, blah. It makes sense to have another v here. Just bear with me here. This is the momentum. This stays constant, right? Same way this was staying constant with half m. So they just want to see, you know, if I have half mv squared, or half mv, and then like the v here I'm going to put here, because so overall just mv as we had before, you know, mv, mv minus v1, blah, blah, blah. So mv is its original momentum, is equal, and we had half v, which is the possible velocity change that we can actually calculate as opposed to what we want to calculate. So that's if it lost all of its momentum, and then so its velocity went all the way down to 0, basically, all of it, then we'd calculate them being together, and the distance they move would be half v, because it would be going from 5 meters per second to 2 meters per second. And we say that it would do this in a second. Because that's how we calculate, like, gas. Just like this would be, if it was hitting an object of the same size, this the only situation would happen. Oh, I know, I don't know about this, to be honest. I don't know why this happened across one second. Never mind. As according to these graphs, where you have v1, v2, like here, where v1, v2, to find out the distance, you do v1, take away v2, so the change in v, times by the time, half v times t. Then to find the velocity, you just divide that. You get half the change in v. So yeah. So we'd have mv half v, which would be the velocity change that can be measured by the change, like the distance that they move together for energy, and that's like the complete thing. And then we'd have, so that's like, they like to think of it as a lovely, like a bowl of energy. And they like to see, okay, what proportion is being given to one thing, what proportion is being given to another. So we have v, and then obviously this is half of the v that they could give. And so the v that you could calculate, so v1, this would be half of v1 now. Only because the end energy would be calculated by halving the v1, wouldn't it? And so you'd get half mv and then the change in v, take away v1, and taking this away from this would give you this with the v, sorry. So the momentum changes, like I said, the change in momentum, so the entire momentum of this, so the total momentum of the system, take away the momentum of one of the components of the system at the end, would equal the momentum gained by the other object, which for obvious circumstances, because momentum is conserved. So if there's a total momentum of 10, and one object ends up with a momentum of 6, then 10 take away 6, you find the end momentum 4. Now, if we presumed all of this into one object, which is what we do with overall forces, really, we kind of presume one of 0 momentum, one of 10 momentum, because the overall change of momentum is 10, and we want to find, the change in momentum for each of these objects because of it. Saying this one has original momentum of 10, but that might not be true. It might be that one object has an original momentum of 4 and the other one has an original momentum of 6, and then the end momentum is 10. And this object may have received a momentum of 1, so 5. This object may have lost a momentum of 1, 4, 5, gone down to 5, so now they meet with the same momentum. And well, they'd have to be the same size to be comfortable with the same momentum. So let's just say this one goes up to 6, this one goes down to 4. Jolly days. Okay. Now this one's lost 2 MV, this one's gained 2 MV, which would keep everything in balance. So the original momentum was 10. This one's end momentum is 4. So the other object must have had a momentum of 6. And that's pure logic. Like, if you're finding out the overall momentum, the end momentum of one, and the overall. Now, how would you be able to calculate that in a situation where you know 2 objects, you know that when they meet the distance that they move, if one had 10, one had 0, then this one had 10, this one had 0, so they basically like swapped momentum. Well, if you knew that the distance they moved would be half the velocity of the 10, and then the mass, I guess, say half v would be the velocity of the move, right? Well, then you have the velocity, or you have half of the velocity of the 10 momentum thing. So if you half the original momentum, half the original momentum, so you've got 5. You know what half v is? You are working out for the original m, so you can work out how much you give to the other one. So you half this velocity as well. So you half the end velocity, but that's what you're working out. So you're cool with that. Its end velocity is 0. You're finding halfway, which is actually quite a bit useful. Because you can't actually find its end velocity, so it's nice to have halfway anyway. It lost all of its energy, so I guess if they didn't have halves, then this would be 10 take away 0, as opposed to 5 take away 5. No, 5 take away 0. No, this would be 10, 5 then, and this would be, what's good because its end is 0, so this would be 0, so 5 take away 0, 5. That's how much it could give, and it did give all of it. So V2, M2 V2 is 10. So this is half because, what's it called again? We're only talking about, well, apparently, only half the velocity change. So this one, velocity changed by 10. So if we wanted its actual MV here, we'd say 10, but we halved it 5. And really, we're basically just halving everything. Because, again, half V is like what we can measure. So we're saying so half of the momentum. How much is lost? Half of the overall momentum. This one's half of the momentum change of this one, and so you'd get half because you've got half the original momentum. Take away half of the momentum change of another one, you get half the momentum change, or I guess half of the momentum end momentum of the other one, then you get half of the momentum of the last one. You would, because everything, if you doubled everything, you'd get MV, take away M, 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 and then V1, which is 0 in this case, is equal to M2 V2. Okay. Now, what they do in, if you collected like things, you'd get half M V take away V1 is equal to half M2. Well, let me just write it somewhere here. So half M V take away V1. Is that right? Half M V take away V1. Change in velocity equals to half M2 V2. Cool. That's the exact same thing being written in a different form. Well, half the change in velocity equal to half M2v2. This is just like the end momentum of them. Now, it's really nice. This is the impulse, or half the impulse. But what have we used so far? We used the distance. We used the fact that distance has to be over time. To get the, basically to get, half of V, and also half of V1. We've distance over time. And we also want mass. So we want mass, we want distance over time. But we also want changes in momentum. So we want a change in momentum, which will make life so much easier. M times change in V, and we calculate the change in V so that we know. So we find the distance that they move together, and we know that that's going to be half of the change in velocity that could have happened, or half of V1 here, and half of MV, and then we get momentum transfer for that one. Okay, now just note that in inelastic collisions, even though energy can be lost, momentum isn't. So, like for inelastic collisions, if you took into account all of the momentum, you get half mv1 half the times the change in velocity would equal to half the momentum change of the second object. So if two objects met, they could disperse energy out in a way that mv is like conserved because it goes in either direction. But this block here is energy. This block here is energy. So it's lost 2 blocks of energy, if that makes sense. Oh. Okay. So objects act in a way that these blocks of momentum loss actually mean something. We can't calculate this by using momentum or change in velocity or whatever. Because the change in velocity will always be not the entire thing, if that makes sense. We don't see like the entire blocks maybe. Now we want to know how much energy is lost. Because let's say we had the interaction where we had this is the change in velocity, we had the half mv take away the end velocity, where the half mv is what we originally added up, so we could, and then we took away like how much energy it had in the end, so basically the energy here, and this was the energy at the end, and we wanted to know, because like you see here, you might think, oh, but momentum is conserved, so maybe nothing actually happened, but what really happens is that there's 2 mv, and then it splits off into half mv this way, and another half mv this way, but it's not, because it's mv, so it would actually be positive mv here, negative mv here, half mv, half mv. The halves are different to the halves, reason for halves there. Sorry, no, because it's 2 plus mv minus mv. So 2 of something's being lost, but it's not momentum, so we can't say mv. But we want this to be positive, so we could say 2 of modulus. We made this modulus, then everything would be cool. So we had v take away v1. I guess if you want to just make your life easier now, you could just, yeah, you could just say, oh, look, half mv, take away mv1, blah, blah. I want all of this to be positive, so you might just like square this times this by v, because this is positive, so this would have to be positive as well, because these 2 are being added. That plus that, if this is positive, then this would have to be positive. So times by v here, times by v here. Oh, look at that, that's easy, right? That's cool. But I'm sure the reason that they times it by v wasn't only just to make everything positive, was it? I guess if everything is positive, then like you times everything by v, that like, I don't know, there's no displacement, no energy, then v0, v1, not v1, sorry, the change in v is 0, that's 0. Then what's good again, this would have the same velocity. I guess the change in v is 0. Then this and then v1 would be same velocity. I'm sorry, the interaction would be nothing. Then, if like a ball hit a wall and the wall didn't deform, and the ball didn't deform, I don't know why I said ball and wall, but whatever, then the interaction would be instantaneous, and so no distance would be covered, no time as well, but that would just make things annoying, so I'm just gonna say the overall velocity is 0. Then this is 0, all of this is 0, so the energy lost is 0 because, well, mv is not the same, but mv squared is the same because the v1 would be equal to v, and so these two would be equal, as opposed to half mv take away mv1, but this v is negative, this is positive. So I guess to speak more accurately, v take away v1, this would be 2, what's it called again? So that would be equal to that, right? So that would be v, but the ball hit the wall and then it came back, would be what happened. No energy was lost, as opposed to an object here goes through that object, losing no energy, and it goes like that. But this situation has no energy loss, so we wanted it to take into account by situations. So we have v, we just times everything by v, because this situation is not taken into account by our momentum model without the extra v's. So we'd have half m, and then v take away v1, but v would be negative v1, so we'd get 2v here, which would be m2v, ignoring the halves because I'll just make everything annoying, but it's m2v, and so we've got a v there and a v there, and we say, well, this is positive, this would become positive because this would be negative, so this would be so 2mv is equal to 2mv, or just a half everything, then mv is equal to mv. Or more specifically, when you get this, you get mv. And that's annoying because NASA suggests that all of the energy is lost. All of the energy isn't lost. It's we take into account with v minus v1 the instantaneity of v1 is 0, so this would be 0, so half mv goes half mv, this would be 0, half mv would be the energy loss, not true. So what we're actually finding is v1, and really what the wall did, well, really what happened here, I don't know, it wouldn't work with this model because basically the wall took all of the kinetic energy, and then the wall gave back all the kinetic energy in the opposite direction because the wall didn't absorb any kinetic energy when it was taken in. Same way if you had like this moving 5 meters per second, 0 meters per second, and then like what's it called again? This went to 1, for example, let's say the wall accelerated 1 meter per second that way. So it pushes it 4 meters per second less. This is pushed up 1, and then it's also pushed up another 1. What's going on when it absorbs this absorbs its energy, this goes down to 1, and this goes down to 1, it goes up to 1, and then like gives back the energy. When it does, this one takes in only so much. No. I had a diagram for this, I'm not going to redo it. Basically I had a diagram here where this gives this one 5 joules, this one gives this one 6 joules, they're joined together, and then this one again 6 joules with 5 joules, but like it switches over, so this one basically goes into the combined form and then out at the end, which happens twice. So the wall would be brought to, I don't know, if it was hit by this one, 2 meters per second, and then this one would be brought to, it was 10, no, it was moved down to 1. Oh yeah. And then what's good again, once the ball's moved to 1 meters per second, it would then be moved again to minus 3 meters per second. That way, this one, the ball went from 0 meters per second to 1 meters per second, it would be moved to 2 meters per second. So the same thing would happen twice because of the energies. But basically energy is kind of like a wave's amplitude, as opposed to, it doesn't take into account its direction, but more just how things add. So the momentum model would work in terms of the velocity going from, I don't know, 5 to 0. That's how much energy it would have lost to that. But then it also would have gained that energy back after, when it went from 0 to -5. 0 is original V, -5, so -5. So its energy back would be the same, basically. It would just gain the energy in the opposite direction. Or the momentum in the opposite direction. 5m, or half 5m. When before it lost half 5m. So that's the energy lost in it. Which is 5 minus 0, and then 0 minus -5. The difference. So here, if you talk about MV, then this would be 5m, half 5m, and V1 would be 0, so half M0, so that would just be half 5m overall. Half of m would be how much it lost, and then on the way back, it 0 originally, half m0, take away -5m, half 5m, so its momentum is gained would be half 5m. It's weird, it's positive, but I guess when you're finding out V minus V1, you're finding the physical difference between velocities, and that's what this is. So you're basically finding the energy transfer. But we know what force is, change in momentum per second, and we find change in force. That's the change in mv per second, right? So that would just be, the force would be mv, and then per second, if that was the change in momentum per second. Or here, if we had change in momentum overall, caused by two objects interacting, well, the overall change in momentum, what's it called again, would be mv minus v1. The overall change in momentum. And remember, like when we're working out work done, we usually have the change in momentum, the force, and then we times by the distance. Well, change in velocity, change in momentum for one object, or just like the overall system. But we can just use force like the combined force, so it takes into account the different masses and stuff, but we can just use one object situation because the other one's conserving momentum is the same thing. So like I said before. So this would be divided by time if you wanted to use force. We wanted to find out the change in momentum as quickly as possible. Now, if you had found out the change in momentum as quickly as possible, but we wanted you have the change in momentum, so force, and then overall force. Then I guess overall force would give us like a similar idea. This will just be every second, so it would be a lot better, I guess. Because once it's all over every second, like we're finding out the change of momentum per second, which is, easier, not easier to work out, but like if we had like an object, we found out its change in momentum rather than its start momentum and end momentum, then we could find out its energy loss, basically, or it's like in this case it's force loss. But the thing what I'm struggling to understand is why we basically take that model, which would work perfectly well, so we and then we times everything by velocity for some weird reason. Well, to change a momentum as the what's it called again? as the start velocity is higher, right? So you're going from 50 and 0. It's something's different than when you're going from 5 to 0 and you're going to 20 instead of 2. Where MV was MV was M50 and then MV1 was M20, and so you're left with 30M as opposed to if you times it by V, the 50 squared would be huge, and that would be huge as well. You'd end up with a value of magnitude 50 times bigger than the already 50 times, 10 times bigger. It would also be 50 times bigger. With work done, we want to know, what is being done, because momentum is stuff pushed together, and this is what is happening. We want to know what could be done.
Where's my glasses?
So we could use impulse in all of these situations. The possible impulse that could be caused, the actual impulse caused, and the impulse left. Impulse. Yeah, I said earlier that this here the half is because we calculate the V from to work out the to calculate the V here because we find the distance traveled and then we half it. We find the distance traveled over the time, and then that would give us half of the V. So after everything else, well, that's actually half of the second V. If you had original momentum, we don't actually want to half the original momentum, so we just add another momentum V, the second V. So it's half the second V. That's what we calculate. The original momentum is fixed. And then we take away the end momentum times by half V. Because when we calculated it, we only calculated half of V1. But we times everything by V just so that this could be true. Just so that it could be we could be comfortable with the fact that half V does not include the momentum. So momentum times by half V. Then take away, then we times everything by V. And we said, okay, half of V1 is what we're finding out. And then, so we're finding half of V1 minus V, take away V1. So half take away the change in momentum. So the half times by the change in velocity times by m to find the change in the loss of momentum, and therefore the momentum the second object gets, or all the other objects get. We times that by v, because originally we didn't want to lose the fact that the momentum is its own thing, and also it makes everything positive, which is nice. Then we can think of it as a concept. We can see momentum and then change in velocity. And then here we've got momentum times by change in velocity. That it should have had, or I guess just momentum and v1 times v. And then this is momentum of the second object times by the change in velocity that should have happened. Or another way of seeing it is that because we're using the mass of the original object, see all the masses are the same for a reason, we're only using the original object to kind of work out what happened to the momentum of the other object. it's actually if half v, then you've literally got v minus, so change in velocity times by half v, which is the total change of velocity that could have happened. This change of velocity is also half of what it could be. So it's weird to think about. This is half v. But we don't quarter it. Okay, apparently. We just say, oh, it makes sense, yeah. So this is the total that what could have happened. This is what could happen. So we're working out the work done by basically saying the m times by the momentum that it should have had if all of the energy was lost. So times by, and then this is like the velocity it should have had, the velocity it actually did get, the velocity it should have had, the velocity of that velocity, how much did it get, and then timesing those two together. And so it's literally giving us the work done, where within the work done equation we have the original velocity. So that if we ever needed, for some reason we had half, so we just have the half mv v1, so we were given the energy of the end, what's it called again, energy of the end of object one. If we had just half mv1, then we could be given the original v1. We know the end velocity, and we know the mass. So we divide and we just be left with half, which would mean nothing to us. But if we wanted to work out the original energy, we could from this work done equation. We divide by the end velocity. We know the mass. We know the end situation. But from that, we'd be able to extrapolate back to the original situation because we'd have half the velocity and we just double that. Or we just find out, half v1, which is like what actually happened, and we'd extrapolate back from what actually happened. So we divide by half v1, so we'd extrapolate back from the distance divided by time, and we divide by the mass, and we'd be left with a velocity. And this, we could square this velocity, times it by half of the mass, and we'd get back to the original energy. And that's the whole idea of energy, and why we use energy the way it is, not using impulse or what's more comfortable, force and impulse and momentum. That would work. That would give us, the proportion there and a proportion there. And the reason why the energy is conserved, very simply enough, energy is conserved because momentum is conserved. Because if momentum, the energy conservation equation is just the momentum conservation equation, like but a bunch of stuff times together. Just like everything times by half, everything times by v, for example, in this case, or everything times by v if we were ignoring the house. But we want to be able to extrapolate back to get us a velocity so that we can work out the original energy supplied, or the energy that should have been supplied. And that just makes, when we work out anything, it just makes not life easier, but it makes what's it called again, understanding the proportion of energy that we've used so much better, because we've times everything by v. So when you're given the first energy and the last energy, and you take these away, and then you're given the energy that was given to the other objects, and the velocity of the other object, and its mass, you can work your way back to find out the velocity that was supplied. So this is the change in velocity, or the momentum of the other object, which I don't think that's right, because the momentum of the other object, no, this is the momentum of the other object. This is, oh, sorry. If we had it here, for example, that's 2 times 2, which is 4. But the change is 3. 3 times 2 is equal to 2 times, no, 3 times this one's change, which is 2. So this would be the momentum of the other object. If we knew the momentum of the other object and we divided it by the energy, and then times that by 2, sorry, that would give us the velocity. From the velocity and the mass of the other object, we could work out the energy that was put in, and so we can literally work our way back and find out all of the energies involved. And that's what we really want about energies. We want this interconnected thing, this like kind of bowl, and then like all the stuff inside it. And we want to be able to work out where all the energy is gone. And that's why we use such an inclusive, I'd say, equation. Also, with this equation, like I said, we use the distance, right? Well, we have force, which gives us like the change in momentum over time. Force gives us change in momentum over time. So mass times change over velocity over time. And we times that by the distance. And it's really nice to find a change in momentum over time, because that means so much more than just the change in momentum. Because if that happened over a really long time, then there would be so much less of a force happening. And so when we're comparing like two objects when they hit, and the amount of, like, I guess if two objects or one object applied a certain force to another object, and vice versa or whatever, and the overall force, you'd want to know, like, okay, what object has, I don't know, so if we worked out the change of momentum here, we're ignoring the v's, then like you'd want to be able to say, okay, this situation had this much of a change of momentum, and this situation just change of momentum. But the when you add momentums, you get them end momentum. So adding forces gives you the end force. But if you have two objects of different momentums, when they're interacting, force is the change in momentum in 1 second, and allows comparisons of momentums. Because when, for example, when momentums interact inelastically, all the interactions are instantaneous, and so it is the instantaneous momentums that meet and react and cause a final momentum. And in real life, these aren't instantaneous reactions. So M1v1 plus M2v2, and then the way they rearrange in a certain way elastically. In real life, that wouldn't happen, but the momentum would be conserved. So we'd want to know, in these situations where it's not instantaneous, what is the proportion of momentum movement around, so we'd calculate the force before, the force of another one, not the momentum before and the momentum after. We'd join them together, we'd work out the force after them and the force like for each of the objects. And this would kind of give us a almost growth from an instantaneous interaction. And so in the instantaneous interaction, we get a certain like change in momentum, and in the other one, we have a change in force. And of course, the change in momentum would be, like, we'd be able to work it out at the end, but we wouldn't be able to work out the change, because obviously in inelastic collisions, they collide, they come out. There's been two changes in the momentums in that. In elastic collisions, sure, there is one. So the force would be overall, like, be connected and go over a certain direction. In inelastic collisions, the forces kind of, they add up only because there's two of each side, but then it cancels. So like if you have a force of 5 applied to one object, a force of 2 applied to the other, overall force has to be a force of 3. Overall force has to be a force of 3. and in inelastic collisions. In inelastic collisions, you'd have, and this is because when they combine, they conserve momentum. In the elastic collision, momentum is conserved, and then when they separate again, momentum is conserved again. So momentum is joined and then separated. So the momentum would be conserved, even if you don't really get it. It's like, in this case, the 3 kilogram goes to 2, then it goes to 4. This goes to 2, and this goes to -1. The 2 kilogram one. These are all meters per second. When it goes, this one goes to 2, and this one goes to 2. This one has a momentum of 6. This one has a momentum of 4, and you get how momentum is conserved in the original situation, right? Overall momentum of these objects together is 10. Right? Okay, and then when they separate again, this one is only feeling the same. It reduces its momentum and it loses the amount of momentum it had before. So it loses 4 MV. This one gains 4 MV. So basically, like, this one has 6, now it has 2. This one had 4, now it has -2 MV. Went from 10, and then went to 4, and then went to -2. This one has 6 MV, and then it went to, because it went to 4, it now has 12 MV. This one must lose 6 MV. This one had 4 MV, and then it went to -2. So it went from 4 to -2. So it lost -6. This one lost -6 as well. So the momentum change on either side is the same, and we know that. That's why they meet at weird points, because the overall momentum change for both is the same, but they have different masses, so the velocity change are different. And then the momentum change happens again, but so the same momentum change, where both of them have the same change in momentum. So this one, 2 times 2. Well, no. They don't have the same change in momentum, but the total change in momentum adds up. The end momentums add up, and then when they change momentum, the change in momentums are the same. 3 times 2, 2 times 3. Their change of momentums are the same. Their end momentums are different. 6 and 4. Their change of momentums are the same. So this one, when it's the change of momentum is the same. When this one loses 6 MV, 6 what's it called again? 6. What's it called again? I don't know the units for impulse up. It loses 6. This gains 6 in terms of momentum. But then this one, they both lose. This one gains another 6. This one loses another 6. So the overall change in momentum is 0. That's what might seem weird. So overall, in the whole situation, we use one object and we find out its original momentum and its end momentum, and so work out its change in momentum, knowing that change in momentum is conserved. So the change in momentum and total momentum as well, the change in momentum for the other object we now know. Because when we work it out using distances. What we actually do, and also this alludes to the idea of work done as well. We know that the change in velocity. So here we got the original momentum of one object, the end momentum of that object, and then the change in momentum, and so the momentum that the other object has. The momentum loss, but so also the momentum the other object gained. And then we know that when we're working it out, we have, this is not supposed to be V1, by the way, that's just a weird school bit there, that's just VV. We have half V here. That's because when we're measuring it, when we want to work it out with the distance, so that we can use force, because force works perfectly with all this. We work out the distance and we divide it by the time. We realize that we will only get half of the velocity change. So this is the complete change in velocity that could happen, such that the complete change of momentum that could happen from mv take away mv1. But when we're calculating it and we want to calculate the change in momentum, so this part here, or I guess this part here, we directly calculate this really because we're using force. We work out that, okay, the original energy, we have to half this because when we're working out this, we only get, for the change in velocity, we only get half of the change in velocity because we use distance over, we use this equation to basically get this equation. So what's really interesting is why do we times everything by the what's called again, v? We times everything by v or the original velocity so that we can extrapolate back when we know the masses and we know the velocity that everything's ended up with, so that we know the velocity this ended up with, the velocity this ended up with, so we can work out the, from, let's say we had the mass of an object, half m, and then we had the velocity of that object, the end velocity of that object, and we knew the mass of the object, we knew the end velocity of the object, and we wanted to know the work that was done to it, and someone told us the work that was done to it. It's not really useful to have this because once we divide by the velocity that it had and divide by the mass that it had, we'd just get half, right? But if we had if it was times by the velocity that it was given, so basically this is the end momentum basically, divide by the the momentum of an object basically, and we are given, so we did energy divided by momentum, and we literally, because the energy is half of the energy that we would normally consider energy, which would be mv squared, and this momentum is also half mv, so we'd have all that, we'd be given v, and we can extrapolate back, timesing this momentum by v, and half, and we can work out what the E is, what their actual E is, not the one that we think would be the normal E. So it's important to have the V in it. Also gets rid of any negatives, which makes life easier. So what we're doing is we have mass of one object, its original velocity, so its original momentum, times by the velocity we can actually measure, which is half V. So times by the change in velocity it would have, the complete change in velocity it would have. So the work, this is again the work that would need to be done, or I guess the work that would need to be undone to it, so that this object loses all of its kinetic energy. So that also explains what the half V is there. Not only is it something that we can measure easier, like if you didn't know the original energy but we knew how much it decreased by, we knew it lost all of its energy, all that stuff. But also this is about the situation occurring and not about the original state. So we don't want to have to be doubling things and all that when this situation happening tells us that this was what happened. So it doesn't really have a mathematical significance, more of a physics significance. and then take away half mv1v, because again this is just everything was times by half v, because this is a change that should have happened. V1 is the change that actually did happen, so it was supposed to go down. It was supposed to what's it called again? I don't know. I mean half. Sorry, no. Sorry. So V1 obviously would be bigger, I would say, than half V, or it could be bigger than half V, which seems a bit weird. But it wouldn't be bigger than V. So half V is what happened, the velocity that was given. Half V is the velocity that was given. Half V is the velocity given. That's good and nice. And then V would be equal to V1 plus V take away V1, which makes sense. This is V2, V1 plus V2, or the change, whatever. And so mv, so we have half v, which is the velocity that should change the velocity that would have happened during the experiment. V1 is the end velocity that the object has. So we're timesing the what's called again, the velocity that change in velocity that should have happened, and the end velocity, which seems a bit weird. Honestly, seems very weird, because it makes sense if this was a quarter, if you half this as well. Because if you half this, then then it would be like what's it called again? If you half this, then we would be getting like proportional, like, V1, the I don't know, 2 was the whole thing. You're timesing it by 1.5, as opposed to having 2, which is half of what it should be 4, times by 1.5, but it's actually like, no, 4, 3, but now it's like 2 times 1, no, 2 times 3, because this was not completely hard. This is not what it actually means. What it actually means is, I know this should have been 4. It's just weird, but we times everything by half, so that this statement makes like explanation sense. mv is the original momentum that adds up overall, so that we can make an equation as such, just this conservation of momentum equation, and then times everything by v, so that when we extrapolate back using energy, we can like calculate the original energy that was given, the original kinetic energy that was given. So that's really useful, so we leave it at that. And then we halved everything, because like the mv squared equation, or the mv, or here even more specifically, the change in mass times velocity minus 1. This equation basically is m times the change in velocity is impulse. So impulse, and then we want velocity. We can calculate that experimentally using velocity. What's going on? This is this v that's being calculated is the original velocity of this. Oh yeah, I was right. What's good again? This is the energy lost. So change in velocity would be the impulse divided by seconds, per second, and then the distance moved, so distance divided by time, would give you the original velocity, half of the original velocity, which is why this is so brilliant, because it always brings you back to the original velocity with experimental situations. That's why it's force times distance. And wait, that's where the work done equation comes from, why it's useful. uh, in 1 hour and 20 minutes. So, well, it took them centuries to work it out. So, 1 hour and 20 minutes to bring it all back together. It seems pretty ideal. It's a lot of this is useful, kind of like this, but also like rate of change of things. So, like, you could also think about it in terms of like force being the work doer, distance being the work done, completed, and then you're doing force times distance to basically say, oh, if I apply a force across 1 meter, I'm doing 1 Newton across 1 meter. I'm doing 1 joule worth of work. And obviously, if you're applying more force and you're moving across a longer distance, then you're doing more work. But you can also think about it in terms of like a momentum loss, momentum gain, and then usefulness bringing extrapolating out of that. Which is probably how like kind of weakly that they did it originally. They probably did a lot of like um differentiation and integration. They probably just thought like like the rate of change of like momentum or whatever. And they're like, oh, change of momentum, that's useful. And then they were like, hey, but we can't like get back to the original like was velocity, like that's important. These are energies, these are jobs done. We don't want to lose the evidence of a job being done. And then they were like, oh, but we work this out physically, like we get all these like halves and stuff, but like the job done is the job done. It's not the job that would have been done if you squared the velocity. It's not like that. It's not a we can't see it. So that's why kinetic energy would be in terms of this. But it also explains why basically the energy given away is the energy also put again that the object originally had, take away the energy that it keeps, and that's the energy that's given away to the environment. But of course the half comes from like the fact that obviously the when the work is being done, the overall like the velocity that the overall change, the overall like the average velocity that the work is being done across, or the distance they travel, per second, is half of the original velocity. If they were like if all of the energy was going to be lost, but it isn't. All the energy usually isn't lost. Some of it's kept, and then some of it's given away, and then it's spread out, whatever. But that is energy work done. Oh yeah. For E equals mc squared, pretty quickly. So that comes from the idea that like when an object with mass turns completely into photons, then obviously wouldn't it have it would have its mass spread out. So its mass m spread out, and so because it's so spread out, that like whole like clump of photons would be moving at the speed of light. Like they would be pushed towards the speed of light. Like the energy they have separated, but they separate it out, but then everything would go in different directions, and they would go to their fastest speed because it's massless. It would go to the speed of light. Um, in that sense, it would be its momentum would be mc, for the whole object. Obviously, the object is scattered everywhere now. Now you might say why is mc squared, but we know that the when it's absorbed by an object, it doesn't move any distance. So if you were like same way with gradient, we kind of like hate zero, something tend towards zero because something that's why it couldn't be zero. But anyway, yeah. So this v is equal to distance over time. Time for there to be no time for the interaction to happen, it would be over zero. So time is approaching zero, but it's not actually zero. But distance is zero. So when it's absorbed, it it moves no distance, but it goes in across a certain time because that's a movement. Just whatever. And so this is zero. This is zero. the energy, basically the energy it keeps is nothing because the photon just disappears and its energy is absorbed in completeness or none of it. And so in that case, because the energy is absorbed in completeness, all of the energy goes to the other object. And so the energy the other object gets is half mv squared, but because it's not half, because there's no distance, so the second v doesn't need to be halved, because when it's giving away its energy, it would bring an object of zero mass if it was going to bring it to its velocity, and if the photon was going to lose all of its energy to v speed of light, basically. So mc squared equals mc squared. Obviously, it might not, because like everything else has a mass, and so everything else's mv would be bigger. But because we are assuming that this object also has a mass, it's just a clump of energy which has an inertia, but it's all moving at the speed of light. Then again, the v here, like I said before, the v here is like it's a way to extrapolate back to the original energy given, but it's not. It doesn't affect this one's like velocity here. So its change in velocity would be v, or it wouldn't be v, but its change in momentum, and v would be equal to this one's change in momentum. And if it was receiving the energy of an object moving at the speed of light with a mass, it would be huge, like amount of energy, change in momentum that this one would have to absorb all of this change in momentum. Probably wouldn't absorb most of it. It's probably why we have photons everywhere, because there's way too much energy. Yeah, that's it. I'm sick of thinking of this like 48 hours a day, 20 hours, 20 days a week. I don't know. I'm done with it. Finished. Like, no way. I'm doing engineering, not physics. Leave me alone. I don't want to code all day. Goodbye.